Hi, 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes, way. Don't delay. Enroll now.
Geeks learning together.
All right, so hi everyone. Let me just quickly check if everything is fine. All right, so everything seems good to me. All right, so this side Ayush Tripathi, DSM mentor and problem setter at Geeks for Geeks, and I welcome you all to this post analysis of last weekly contest 112. So, before starting the contest, I want you guys to rate the entire contest on a scale of 10. And in case if you are rating less than or equal to 3, then please justify your reasons as it would help us to improve the upcoming problem set. Okay, hi Shubham. Hi Rohan. Okay, 9. First question is too frustrating for me. Okay, Ankit. You can check your score or a rank on a leaderboard. Was able to solve last two. Last problem was not a very much difficult. It's like a simple knapsack DP. First question is frustrating. First question is not that much easy, I can say, but it's require a very standard technique. We will discuss it very soon. For second question, I was getting TLE. I guess the second question is the best problem of the entire contest. Binary search first. Okay, so let's just share my screen first. So hope the screen is visible to you. So the first problem was what mean do you mean? Okay. Or so in this problem, basically we have an array of size n and a number k, and our task is to select two distinct indices and multiply the value at those indices by k, and we are only allowed to perform this operation exactly once, and our task is to check that whether it is possible to perform the operation in such a way that that the mean, or we can say average, both are the same thing, of the resulting array is equal to given value x. So is the problem statement is clear to everyone? So do write +1 in the chat if the problem statement for the first question is clear to everyone. All right, so let's just move to the board. So we have an array ARR of size n. So ARR of 0, ARR of 1, ARR of 2, and so on till ARR of n. minus 1. And in one operation, we are allowed to select two distinct indices and multiply the value at those indices by k. And after performing the operation exactly once, our task is to check that whether it is possible to make the mean of this array equal to x. So we want mean, or we can say average, is equal to x. So tell me, when the mean of this entire array equal to x, so it will equal to x when the sum of this entire array, so I can say sum of a is equal to n into x. So is this thing clear to everyone, that when the sum of the entire array is equal to n into x, then mean is equal to x, because the formula for mean is equal to n into x by n, sum of array divided by number of elements, which turn out to be x. So hope this thing is clear to everyone, that if the sum of entire array is equal to n into x, then their mean would be equal to x. All right. So, and in one operation, we can convert any element arr of I into arr of I into k. So what a difference every element I contributes. So let's say it is temp, and this temp is nothing but a difference. So the difference is equal to arr of I into k minus arr of I. So every element I contributes this extra sum in an array if we apply the operation on the ith element. So is this thing clear to everyone? Please write a +1 in the chat if this thing up till here everything is clear to you. Okay, explain temp. So this temp is nothing but the difference that ith element contributes if we consider ith element for operation. So this is the like value of element after we multiply it by k, and this is value, original value, initial value. So their difference is uh, subtraction, their subtraction. And I can also write this thing as arr of I into k minus 1. Okay, you don't need to apply any division operation. All right. So the value of a temp, that is contribution of ith element, is this one, arr of I multiplied by k minus 1 if we select ith element for operation. So, and we want to achieve this sum, right, n into x. So what we will do, we first subtract the sum of entire array, initial entire array, from n into x, then we get what sum we want to add, right? So more formally I can say this variable sum denotes that okay, So this variable sum denotes that extra value that we need to add, right? So the value of this sum is nothing but n into x minus the sum of initial array, which is a of 0, not a but actually arr. So arr of 0 plus arr of 1 and so on till arr of n minus 1. So is this thing clear to everyone? That is, we want to add this extra sum in our in an in our array such that the sum of entire array will become equal to n into x. So this is nothing but n into x minus a sum of initial array. All right. So now we know the contribution of every element that it will contribute. That is extra value that it will contribute, and we know the sum that we want to achieve, right? So now this entire problems boil down into a very standard problem where our task is to check that whether in an array there exist two elements such that their sum is equal to this sum. So I hope this thing is clear to everyone, and to solve this standard problem we use a hash set, and it is actually a very standard two pointer problem. So let's just denote a new array. We can say array A. So this array A denotes the ith element of this array A denotes the extra value that ith element adds in our sum when we consider ith element for iteration. So then a of 0 comma a of 1 comma a of 2 and so on, a of n minus 1, and a of I. So a of I is nothing but arr of I multiplied by k minus 1, or we can say temp. That is the difference that ith element contributes. All right, and from this array we want to select two elements such that their sum. So I can say a of I plus a of j is equal to sum, this one, this sum. All right. So and this is a very standard problem, and the idea is to use a hash set, right? So or you can also use a hash map. So we know the value of ai, which is equal to arr of I multiplied by k minus 1, right? So like the ith element contributes this extra value, and we want this sum. So for the next element what we want, so we want some element a of j such that the contribution of a jth element is equal to sum minus a of I. So is this thing clear to everyone? Why 0? Where I have written 0? So we want to find a of j the such that its contribution is equal to sum minus a of I, so that we pair these two element a of I and a of j. So the contribution of a of I is equal to arr of I minus arr of I into k minus 1, and the contribution of j is equal to sum minus a of I. All right. So if we pair a of I and a of j, then what we get? So like a of I plus a of j. So we know a of I will remain as it is, and a of j is equal to a of sum minus a of I. So this turns out to be sum, and this is something that we want. So please write a +1 in a chat if this thing is clear to everyone. Like this is the best explanation from my side, I can say. And if I show you the code, then it will be more clear to you. Okay, all right, Rohan. So to find a of I and a of j, we don't need to the iterate two times over the array. That is, we are not allowed. We are don't need to uh, run our two for loops, one for I and one for j. We can use a hash set, or we can say hash map. So what we can do? So we started traversing the elements from left to right, and we know the value of a of I. So we check that whether we have encountered this value previously or not, and if we encountered this value previously, then I will simply return true. Otherwise, what we will do, we simply insert a of I in our set, so that a of I may be paired with some element that we encounter in a future. So this was like the entire solution, and let me show you the code, then it will be more clear to you. So here this is mean function is given to us. Okay, so all right guys, so tell me that do I need to implement the solution from scratch, or like showing the implementation is enough? Because I believe in explanation rather than implementing the solution from scratch. This is kind of a wastage of time, but definitely I will go with a majority audience. So what you want, that do I need to write the entire code from scratch? Okay, okay, definitely provide the code. So see, the first thing that we want to do, and then what we are doing, we are subtracting the initial sum of the array. Then here I am subtracting the initial sum of the array, then like declaring a set over here. Then this variable temp is nothing but like the difference that ith element contributes. Then iterating over the initial array, then this is the extra contribution of current element from arr of I, which is it into k minus 1. This is the extra value that the element contributes when we consider this element for operation, right? So we wanted to make this sum. So then here I am checking if sum minus temp already exists, then I am returning true over here. Otherwise, I am inserting this temp because this temp maybe contributes with some other element in future. That's why it is necessary to insert a temp. And after considering all the possible cases returning false over here. And this is like a very standard technique to check that whether uh, two pairs exist with a desired sum or not. So I hope the entire explanation is clear to everyone. Okay, yes, Nitish, you can also like see the Java solution. Pointer is the same than array. Okay, you can also use a two pointer technique. That is, first sort the array, then initialize one pointer in the beginning and other pointer at the end, then keep on moving the pointers while you do not encounter the desired sum. So let me just try to submit this. Accepted. Or let me just quickly share this solution. Okay, so this is the entire solution. Okay, let's just answer a few queries. Okay, so someone asking why it is ARR of I into k minus 1. So like why it is ARR of I into k minus 1. So see, we want to check that what extra value the ith element contributes if we consider ith element for operation. So initial sum was ARR of I, and if we perform operation, then the value becomes ARR of I mm, into k. So the difference, or we can say the extra value that ith element contributes, is their difference. So which is ARR of I into k minus ARR of I. So we can also write this as ARR of I into k minus 1. So now let's just move to the second problem, which was named as gold is old. Okay, makes sense. So, and also believe me guys, this is like a few of the best greedy problem that I have solved. And this uses a really a very interesting idea. So let's get it started. So in this problem we have some initial number of experience points and n quest, and we also have two arrays, experience required and experience gain, where the ith element of experience required denotes the minimum experience that we require to complete ith quest, and the ith element of experience gain denotes that the point of experience that we get after completing the ith quest. And we are only allowed to complete at most k quest, and our task is to determine the maximum number of experience point that we can accumulate. So let me just hide the solution. So is the problem statement is clear to everyone? Please write a +1 in a chat, or I need to explain it again. All right, only getting a single +1. All right, so let's just move to the board. And the idea here is to keep on adding the quest under consideration, while the current experience is greater than or equal to the experience that we required. And once we get some quest for which the current experience is not enough, then we are forced to complete some quest. So which quest it is optimal to complete? So it is optimal to complete the quest with the maximum experience gain value. So is this idea is clear to everyone? Okay, so explaining it one more time, or last time, please pay more attention over here. So the idea here the idea here is to keep on adding the quest under consideration while the experience required is less than or equal to current experience. And if the current experience is not enough, then we are forced to complete some quest to open the upcoming opportunities, right? So which quest it is optimal to complete? So it is optimal to complete the quest with the maximum experience gain. Okay, so let me just quickly move to the board. So what are the things that we have? We have a number of quests and some initial experience, and two arrays experience required of size n, and experience gain. So I'm going to write the entire idea for this problem. So it was a great round of fun of solving. Okay, Arjit. So the idea here is to keep on adding the quest under consideration while experience required, that is I, is less than or equal to current experience, and the initial value of a current experience is equal to initial experience. So this current experience is kind of a variable. Current experience is equal to initial experience, And uh, once we get some quest such that is if quest, or not quest actually, but if experience required is greater than current experience, then in that case we are forced to complete some quest to consider the ith quest under consideration. So like which so then which quest is optimal to complete? So it's optimal to complete the quest with the maximum experience gain. And to check that which quest is giving the maximum experience, we use a priority queue, or you can also use a hash set, or we can set. So in my implementation I am using set, and you can also use we can say heap or priority queue. So in my set I am using in my implementation I am using set of pair of int comma int pair of int comma int, where the first value is experience gain, and the second value is index. So while current experience current experience is less than required experience, and k is greater than 0, because we are only allowed to uh, complete at most k quest. Then what we do, we simply we simply complete the last quest of this set. So if p denotes so let's say the name of our set is st. So if p denotes the last element of this set, which is nothing but minus minus st dot end, and this is a kind of a pointer, so we have to dereference the value, so that's why using a star operator. So now p is storing the last element of set, so we simply add add the experience gain in our current experience. So current experience plus is equal to p dot first, and see here the first value is storing experience gain, that's why adding p dot first. And since we are allowed to complete a quest at most once, so we need to erase p from our set. So st dot erase p, and also we need to decrement k, because we have completed one quest. And after this while loop we check if current experience is greater than or equal to experience required. Experience required of I, then we can add the ith quest under consideration, right? So then we simply insert st.insert experience gain, comma I in our set. So this is the entire approach. So like recommending you guys to read the entire approach and go ahead with your queries. Okay, explain the approach first. Naman, I am explaining the approach only over here. Easy question was most toughest today. Okay. At each time we are choosing one with the maximum experiences, so we can use a hash map. Yes, Archit, makes sense. So is this explanation is clear to everyone? I solved it. Solved it. Yes, you can also use a max heap, but set because of the limited required operations. What if experience required is 10 and gain is equal to 100? Now I don't have a 10 initial experience, but after getting some more quest we will have a 10 experience, then we will leave that 100 gain. Okay, not actually like leaving that 100 gain. Actually, I'm not getting your question, Gaurav. Can you please elaborate it properly? So let me explain you again. So see, the idea here is is to keep on adding the quest under consideration while the experience required is less than or equal to current experience. So see, here we are not performing the quest. We are only performing the quest. We are only performing the quest when we encounter some quest with a greater experience required. So then we are forced to perform some quest. All right. And one more thing to consider, all quest for which the required experience is less than or equal to current experience, we sort the quest in ascending order of experience required. So let me just quickly add that thing as well. So we need to sort quest in ascending order of order of experience required. So see, when we encounter some quest with experience required greater than current experience, then we know all the future quest also having a experience required greater than current experience, right? So now we are forced to complete some quest to open the future opportunities of considering the quest. So which quest is optimal to complete? So it's optimal to complete the quest with the maximum experience gain, and that is what we are doing here. Then checking if the current experience is now greater than or equal to experience required, then we add ith quest under consideration. Okay, see, first we are adding the quest under consideration if the experience required is less than or equal to current experience. Here we are not completing the quest, we are only completing the quest when we encounter some quest with a greater experience required, because we know all the future quest is also having a greater experience required, so we are forced to complete some quest. So which quest is optimal to complete? So it's optimal to complete the quest with the larger experience gain, and we need to check for this additional constraint, which is k. So this was all about explanations and observation. Let me show you the implementation of this entire problem. And this is enough explanation from my side. So this is the function given to us, max xp. Then here I am defining mp as make pair, then our answer, and this answer is nothing but current experience. So this is current experience. Then here we have a set. You can also use a, a heap, and here I am using set to extract the quest with the maximum gain experience. Then here we have a vector of a pair of int comma int, and this is because of a sorting purpose. We need to sort the quest in ascending order of experience required. Then updating this vector v with experience required comma experience gain, then sorting this in ascending order of experience required, then running a for loop and checking if answer is greater than or equal to the experience required, and this answer is nothing but current experience. So more formally I can say, if current experience is greater than or equal to experience required for ith quest, then we add the ith quest under consideration, or we need to add the ith quest in set. So that's why making a pair with experience gain comma index. And once we encounter some quest with experience required greater than answer, then we are forced to complete some quest to explore the current and future opportunities of adding the quest under consideration. So while answer is less than the experience required, or we can say current experience is less than experience required, and k not equal to 0, because we are only allowed to complete at most k quest. And of course, while set not become empty, then completing the last quest of set and adding the experience gain in our answer and erasing that quest from set and decreasing k from here, then checking if the current experience is greater than or equal to experience required, then we add the ith quest under consideration. All right, and after iterating over all the n quest, we need to check that whether we are left with some value of k or not, or we have some element in our set. So we are allowed to complete k quest. So that's why checking if k not equal to 0 and there is some elements in a set, then we greedily select the quest with the maximum experience gain, which is the last element of set, then adding the experience gain in our answer and erasing it from set and decreasing the value of k, and then we simply return this answer, that is the current experience. Right, one way can be shorting. Okay, let me just check. I had some doubt if there are some way using custom comparator and shorting. Okay, but I don't think you need a custom comparator. Why you need a custom comparator where this shorting we can directly short in this way? So let's just try to submit this, and the time complexity is n log n because of this shorting. Uh, so this was all about explanation from my side. Okay, so please write a +1 in a chat if this entire solution is clear to you. And if you guys have still some doubt, then go ahead with your doubts, or you can also write your doubts in the comment. But this is the best explanation from my side, all I can say. And analyze this entire algorithm. What I would suggest ki analyze this entire algorithm and the implementation. The problem is not that much difficult, but I can say a bit tricky, but it's not that much hard to not understand. So let me just quickly share this entire solution to you. All right, guys. So moving on to the last problem of today, which is a minimum price. So let me just share my screen. So how many of you are able to solve this problem? And the problem is like uh, not that much difficult, and actually like a variation of a knapsack problem. Uh, all right. So the problem was named as a min price. In this problem, we have n items where the price of ith item is denoted by p of I, and there is also some bonus on all items. And if we buy ith item, then we get f of I items free of cost. And with this, our task is to return the minimum amount of money that we need to buy at least n items. And if so, the important thing to note here is that if we won't get fi items for we won't get fi items for free if the ith item has been received free of cost. Yes, yes, Archit. So let's just explain this sample test case. So where the value of n was 4, then 10, 20, 5, 3. So n is equal to 4, then array p as 10, 10, 20, 10, 20, 5, 3. Then array f was 2, 0, 1, 1, I guess. Yes, 1, 1. So 1. And our task is to return the minimum amount of money that we required to buy at least 4 items. So the minimum amount that we required is 8. We purchase this item, this third item, and this fourth item. And after purchasing these two items, we get 2 bonus point. One for third item from third item and one from fourth item. So from these 2 bonus points, we can achieve these first. Let me change the color. These first and second item for free. We don't need to pay anything for first and second item, and this is the minimum possible cost that we required. And now we have 4 items. We purchased 2 items and we get other 2 items for free. So is the problem statement is clear to everyone? Please write a +1 in the chat if the problem statement is clear to you. All right, Archit. Thanks for confirmation. So we need to find the minimum cost. Minimum cost, right? So not only in this problem, wherever when you have to maximize something or minimize something, then there can be only 3 possible solution exist. Uh, Greedy solution, binary search, or dynamic programming. Dynamic programming. And it's always optimal to follow this hierarchy, because there might be a case when your dynamic programming or binary search solution requires some greedy observation. So it's always optimal to follow this hierarchy from top to bottom, right? And the probability of failure of your solution is increases from top to bottom. Okay, not increases but actually decreases from top to bottom. Greedy solution is having a more probability of a failure, while the dynamic programming solution is having a kind of a very less probability of a failure, because dynamic programming is nothing but recursion plus memorization, right? And recursion is nothing but kind of exploring all the possible configurations, or we can say exploring all the possibilities. So the dynamic programming solution is having a very less probability of failures. And specifically for this problem, greedy solution won't work. So tell me, what is the best greedy approach according to you? waiting for your uh, comments, I can say. Like, what is the best greedy approach for this problem according to you? And don't forget to consider that we are not getting a single item when we purchase the ith item. We are getting f of I. So let me write over here. What are the items we get if we purchase the ith item? So the number of items that we get is f of I plus 1, because we have purchased item I and we get fi items for free. Uh, Short by minimum cost based on free items. Okay. Uh, Not any solution is same as my expected solution. Short them by minimum cost. It does not make sense by shorting them in minimum cost, because it is not a single item associated with ith ith element. Okay, the best max free items. So like 2 pointer plus shorting, I guess. Okay, does not make any sense. 2 pointer plus shorting. Okay, not getting your point, Arjit. Anyway, let me explain you the best greedy approach. So the best greedy approach. So let me just write over here. Yes, Rohan, we need shorting. So the best greedy approach is to short the items in ascending order of price required for per item. So more formally, I can say uh, short in ascending order of price required for per item, or we can say single item, that is fi plus 1. If we purchase the ith item, then the number of items that we get is fi, which is a bonus plus 1 items. So we short them. The number of the price of per item. So fi plus 1 divided by p of I. So is this thing is clear to everyone that why I'm shorting in this way? So that we get the price for a single item, and this is a kind of a best greedy approach according to me. I think short by ratio. Yes, exactly, Rohan. Okay. Okay, kind of a knapsack. How you come to this? Okay, so like, okay, so I guess it is not uh, fi plus 1, because the fi plus 1, okay, because fi plus 1 items cost pi, we can say pi bucks. So for one item, the cost, so fi plus 1 item. So the cost for one item is p of I divided by f of I plus 1, and it's actually kind of a reverse. So let me change this thing. So it is actually pi by fi plus 1. Pi should be in numerator. Yes, Jashwant. Sorry for that. So is this thing clear to everyone that this is the best greedy approach? Sorting in ascending order of a ratio. Please write a +1 in a chat if this approach is clear to everyone. Also, it won't work, but let's elaborate that why the greedy approach won't work over here. Uh, all right, so we short in ascending order of this ratio, but this solution won't work because we are not allowed to break the ith item. We are not allowed to break the ith item. So that's why this solution won't work. But if we were allowed to break the ith element, then definitely this greedy solution is the perfect solution for this entire problem. And the reason why this solution fails is because we are not allowed to break the ith item, or we can say uh, ith price. We cannot extract a single item from ith element. That's the reason why greedy approach fails, because there might be a case when the ratio is 2.5, and for next the ratio is let's say 4. So you select the shortest minimum ratio, but if the so let's say the number of items associated with this ratio is 5, and the number of items associated with this ratio is uh, is 2 only. So for 2.5 it's not actually 5, but 4 items associated, and for the second ratio 2 items is associated. And if you select the smaller ratio, then you are forced to select all the 4 items, and you are not allowed to break the price. So if required is only equal to 2, and you are selecting the smallest ratio, so the cost that incurred is 10 for the smallest ratio and 8 for the second smallest ratio. So this is second smallest ratio is optimal to select because we are only require 2 items. So greedy solution uh, failed over here. So please write up +1 in a chat if this thing is clear to everyone. It's taking a lot of efforts, guys. If the ratio was perfect in all cases, then the greedy solution work. Okay. Not getting your question, Archit. Anyway, so the greedy solution fails for this problem. Now we are left with binary search and dynamic programming. And I don't think there exists some optimal strategy to find the check function for binary search. So binary search also won't work over here. Now we are only left with dynamic programming. So let's see what are the parameters that so let's see what are the parameters changing parameter. So we have programming, right? So the only parameter that we need to memorize is index. So let's say ID and a bonus point. Then for every index ID, we have two options. That is, we uh, either buy the item. So let me change the color. Either we purchase the item or we use a bonus, right? So like what is the next transition if we purchase the item or if we use the bonus? So the next transition, so let's say the name of our function is memo as per my implementation. So the next transition is memo id plus 1, and then we get bonus. So for the next index, the bonus is equal to bonus plus f of id, because we have purchased the item with index id. So our bonus will increase by f of id, and since we are purchased the item, so we need to pay the cost. So this is nothing but p of id, p of id. And if we use the bonus, then the next transition is a memo of id plus 1, because we are only allowed to select the item for once. Then the bonus will decreased by 1, because we have used one bonus to purchase the item with index id for free, so bonus minus 1. And since our task is to minimize the cost, so we select a minimum of these two possibilities. All right, so I hope this thing is making sense to everyone. So let me just write it in more clear way. So our answer is equal to minimum of these two transitions, right? So our answer is minimum of these two transitions. And since it is kind of a knapsack problem, so the problem is having overlapping sub problem. So we can memorize this using an array. So now let's analyze the time complexity. So the value of n can be up to 500 and fi can also be up to 500, right? So the value of id can go up to 500 only, right? And what is the maximum value of a bonus? So the maximum value of a bonus, that is f of I, is less than or equal to 500. So in worst case, the maximum value of a bonus can be up to 500, where we have 500 items, and for every item the bonus is 500. So this is the maximum possible value of a bonus. So we have to create an array of size int. Let's say we named our array as tp of 500 into 25 uh, 250,000, right? And this is kind of around 10 to the power greater than 10 to the power 8. So greater than 10 to the power 8. So definitely this is not feasible, and you will get an TLE. So we have to do something better, right? So here now we need to draw some observation. So tell me guys, if the value of a bonus is greater than 500, do we need the bonus for which it is greater than 500? That is the number of items. Actually not, right? So what we can do, instead of keeping track and storing all the bonus, we check for every index ID. So like if if ID, not ID but actually n minus 1, this is because of a zero based indexing, minus ID and plus 1, we need to consider the current item as well. And if the number of items that are left is less than or equal to bonus, then this means we can achieve all the items free of cost, so we don't need to uh, purchase them. So in that case I will simply return 0. Or in more simple way, I can also write this n minus 1 minus id plus 1 as n minus id, because this get cancel out, minus 1 plus 1, right? So if n minus id is less than or equal to bonus, then I will simply return 0. We don't need to pay anything. Hope this thing making sense to you. All right. And now the maximum value of a bonus can only be up to 500. So now this bonus is less than or equal to 500. Okay, why bonus minus 1 when we have purchased it? So see, for the next transition I am using bonus, not purchasing the item. For this transition I am purchasing the item, so here not incrementing, not decrementing bonus, but rather than that we have to add the bonus of a current item, which is f of id. So this was all about explanation and observation, and now let me show you the implementation. But we will get a bonus. Okay, but we will get a bonus only when we purchase it. So yes, we are purchasing it. So see, adding this cost p of id, that means we are purchasing it, and then that's why here adding the bonus in bonus. So this is our given function minimum cost with n p vector p and vector f. Then here we have our dp 2d dp array for memorization purpose of size 500 into 1000 plus 1. And why it is not a 500? Because this bonus can be negative as well, right? Because eventually we are subtracting something from bonus, so this bonus can be negative as well. So and we don't have a negative index in an array, so that's why adding some constant to prevent the negative values. And this is a kind of a very standard technique to prevent to memorize the negative values by adding some constant. You can also add some constant over index, but you don't need this, because we know the index, the value of I is no more less than 0, so you don't need to add constant over here. So what is our base case? So if we have explored all the n items, then checking if a bonus is greater than or equal to 0, then I am returning 0. That is an happy case, kind of. Otherwise, if a bonus is less than 0, then this means we we received some item free of cost and without using a bonus. So in that case, that configuration is invalid. So to avoid such a configuration, I am returning a very large value. In this case, it is a 10 to the power 18. Otherwise, checking if the number of bonus is greater than or equal to number of items left, in that case we don't need to do anything, so simply returning 0 from here. Otherwise, this is our answer, which is dp of I comma bonus plus 1 plus 500. Then if answer is not equal to -1, and it is kind of a memorization part, then simply returning answer. Otherwise, returning minimum of these two transition. In the first transition, we are purchasing the ith item, and in the second transition we are using a bonus, then simply returning answer. So let's just try to submit this. All right, accepted. And the time complexity is 500 into 1000. So let me share the solution. Okay, not this one. And you guys can go ahead with your doubts. And wrapping the session in 1 minute. Okay, so this is the complete solution, and this was all about today's session. Thank you so much for joining. And in case if you have learned something new, then please hit the like button. And your feedbacks are really important for us. It helped me to improve the upcoming session. So, all right. Thank you so much.